It's an invisible force that we put to work, trapping bubbles in a soft drink, turning liquids into foamy cream, and generating the most damaging force in an explosion. Get ready to spend some time with modern marvels under pressure. Pressure is hard at work all around us. An invisible force that makes things move faster, change consistency, or raise and lower temperature. Pressure is often hard to see, but it can be measured, whether it's in liquids, in solids, or in gases. Pressure is registered in pounds per square inch, or PSI. That's literally the weight of 1 pound pressing down on 1 square inch. Add weight, and the pressure goes up. The water that comes from your tap, that's about 35 psi. The water shooting out of a fire hose, about 100 psi. Nobody understands the power of PSI like firefighters. Engine 22 of the Danbury, Connecticut Fire Department is a state-of-the-art mobile firefighting platform designed to do one thing: generate flame-killing water pressure. Lots of it. Engines like these are technological marvels, capable of delivering more than 1,200 gallons per minute via multiple hose connections. That's because the engine's internal pump creates enormous pressure that can push water out at top speeds. Engine 22 only carries 500 gallons, so these high-pressure hoses are going to need more water, fast. In most fires, that water comes from a fire hydrant. A 5-inch diameter supply hose locks into the town's water system. The pressure is on, and the hose springs to attention. But municipal fire hydrants are unpredictable, delivering water at varying pressures. So the fire engine itself juggles the inflows and outflows, keeping the pressure constant. Tackling a fire from a ladder truck adds another layer of complexity. The engine has to generate additional PSI to compensate for its height over the ground.
22 driver, 24, water's on the way.
It's like pumping 1,000 gallons of high-pressure water up a steep hill every minute.
You have a big fire, you need big water.
Firefighters can't handle this volume of water by hand.
We could unsheathe all the shingles off this roof. You're putting 1,000 gallons of water out at 80 pounds per square inch. That's a lot of force. It's an awesome amount of power.
Nothing is more critical to this high-pressure offense than a strong defense, and it comes from a fire hose. A flexible cylinder lined with synthetic rubber.
This is a rubber extrusion machine. We're making a tube liner. So the rubber actually works really well in the fire hose because it enables the fire hose to dilate and swell and stretch under pressure. It also obviously provides sealant for the water to transfer.
All American Hose in western Pennsylvania uses about 2.5 tons of synthetic rubber every day. This liner will fit inside a sturdy outside covering made of tightly woven nylon. The weaving machine spins at 100 RPMs. The weave is so tight, the machine's output is only 2 feet per minute. After weaving, each jacket is manually inspected for any defects that could cause the hose to weaken and burst under firefighting pressures. The jacket and rubber liner come together on this 100-foot-long table.
A fire hose is usually made of three sections. One is the inner rubber liner, which we insert into the inner jacket. And then we take that inner jacket liner assembly and we insert it into an outer jacket. That protects the hose whenever it's under pressure. It also protects it when it's under fire conditions.
Pressure seals the deal with an 80 psi hot steam treatment for 15 minutes. The steam expands the hose to operating size for the first time and activates an adhesive that binds the inner layers together. The steam, heat, and pressure make the fire hose even more rugged. With the addition of alloy couplings, the fire hose is almost finished. But first, it must endure a proof test where it's subjected to 800 psi. That's 2 times greater than the maximum that firefighters will ever need. Why? Because pressure can spike unexpectedly when hoses are twisted, crimped, or run over. Some hoses undergo an additional burst test over 1200 psi. That's enough to break them open. But the way this hose is designed to burst, along its seam, it could handle even that.
Pumped up the hose to the burst pressure, and when the hose bursts, we want it to burst longwise so it's safe like a banana. If it bursts in the cross section, then it can be a loose cannon. Get out hose flying all around.
It takes more than 1200 psi to burst this hose, a key test of its ability to withstand enormous pressure. But even to those of us not battling fires, water pressure plays an essential role. When you turn on the tap and water flows out, it's thanks to water pressure. But how does water pressure work? And why is it so reliable? As a liquid, all water naturally flows downhill, picking up power and pressure as it travels. It's the same basic way water gets to your house. A water tower is simply a large water reservoir, elevated to generate pressure and propel water into your kitchen sink.
Water towers use the most patient force I know, and that's gravity. All you have to do is rely on the mass of water to push it through the pipes, and for the most part, you're in pretty good shape.
Your typical water tower holds more than 1 million gallons, but its height is its most important feature. For every 2 feet that water is raised off the ground, it contributes 1 more pound of pressure, or PSI, to the system. A water tower must be tall enough to push water through a network of pipes and into surrounding homes and businesses. Most cities aim to generate pressure between 50 and 100 psi. Water towers are usually taken out of service for maintenance once a year. This gives us a rare opportunity to step inside its pressure-creating construction. This tank is over 90 feet in diameter, and it can hold 1.5 million gallons.
When the tank is full, there would be 35 feet of water above us.
In Loudoun County, Virginia, Caldwell Tanks is now constructing what will be the country's biggest water tower site. These 2 massive 3 million gallon towers are half steel plate and half reinforced concrete.
The pedestal has a diameter of 64 feet and 12-inch thick walls all the way around. The pedestal height is on the order of 110 feet, including the dome that is on top of the pedestal.
When it's completed, the 500-ton tank will be hoisted up to the pedestal's dome and locked into position. This 116-foot diameter tank will deliver 50 pounds of pressure into the local water system, serving 15,000 households. But what happens to your water pressure if you live in a building that's taller than the highest water tower? That's a problem that New York City first faced more than 100 years ago, when it began to grow taller. There wasn't nearly enough water pressure for the topmost floors. The solution became an icon, a water tank for every building over 80 feet.
Water tanks are old school, but they still work.
Water tanks like these are replaced every 25 years. The job has to be completed in less than a day. A challenge American Pipe and Tank is ready to take on.
While this tank is empty, this building has no fire protection. So it's pretty critical that gets back online as soon as possible.
The team spends the first 2 hours dismantling the old water tank.
Watch it.
Next, they assemble a barrel large enough to supply this 9-story building. 5,000 gallons should do it. The team erects a circle of staves and then tightens them into position by a series of hoops. All of this while dangling more than 100 feet over the pavement. In New York City, all water tanks, old and new, are made of wood.
Wood is a great material for an outdoor water tank. Wood is a natural product. It breathes. It does very well outdoors. When you actually look at this tank from the top, you will look down and you will see a true circle, perfectly milled and installed like a big jigsaw puzzle.
Like all water towers, once completed, the tank will require very little attention to do its pressure-generating job.
The water tank is a very maintenance-free type of system. A small pump in the basement fills the tank and gravity just does the rest.
While New Yorkers are proud of their rooftop water tanks, some landmarks prefer to keep them out of sight. The Empire State Building was one of the first skyscrapers to hide its water up top. So even if you don't see them, water towers and rooftop tanks are up there, providing constant water and steady pressure. Countless aspects of our everyday lives are under pressure. We harness water pressure and store it high in the air until we need it. We bottle up air pressure and hold it in aerosol cans. It may be everywhere, but pressure is not always under our control. Explosions. This is pressure gone wild. An explosion causes rapid expansion, which gives birth to an unpredictable pressure wave that can travel over long distances. But what's really going on here? Imagine a pebble dropping into a pond. The ripples move out at a steady pace. An explosion is something like this, but in the open air, and not at all steady. Shock waves from an explosion can only move as fast as the speed of sound, so they bunch up, and that's what creates a wallop-packing pressure wave. But pressurized gases aren't always destructive. On a much smaller scale, we even bottle air's explosive pressure and enjoy it, bubble by bubble. Avery Beverages has been putting the pop in soda pop for more than a century.
If you want to see what 300 pounds of pressure is like, I can open a valve here. It's pretty loud, though. I'll warn you ahead of time.
Rob Metz is the mastermind who keeps these decades-old machines running.
We're an old-fashioned soda company, and it's, as you can see, handmade. And we still make our soda the way it was done years ago.
That means first mixing up a batch of flavored syrup, and then adding the other half of the recipe, the fizz. The bubble